Hello everyone, my name is Can Coşkun and today I will present my Phys102 Lab Project about investigation of the relationship between the electric permittivity and sound density in a custom-built parallel plate capacitor. The main objective here is to observe the dielectric decrement phenomenon. Theoretically, when we add the sodium chloride to water, the sodium ions and chloride ions create intense local fields. These fields capture water molecules into solvation shells, preventing them from aligning with an external electric field. As a result, the solution's ability to polarize decreases, which should lead to a lower capacitance. Now let's look at the experimental setup in detail. To build this parallel plate capacitor, I use several specific components. These are two identical copper plates measuring from 9.7 centimeters by 5.4 centimeters. To keep this geometry consistent, I fixed them at a precise distance of 15 centimeters apart. To secure these plates, I used specialized aquarium silicone sealant. This was a crucial step because aquarium silicone is chemically more stable. After applying the sealant, I left the entire setup to cure for full 24 hours. This ensured the bond was perfectly ironed and wouldn't release any trace residues into the water that might interfere with our dielectric measurements. To ensure high precision in our saltinity levels, I used a digital scale to measure the sodium chloride increments, 0.5 gram, 1 gram and 1.5 gram with absolute accuracy. I placed 10K ohm resistor in series with the capacitor. The specific resistance was chosen to slow down the discharge rates, which is giving us enough time for manual measurements. I used a digital multimeter set to voltmeter mode to monitor the potential difference across the plates in real time. I used a DC power supply to charge the capacitor to an initial voltage. For security and low resistance connection between the power supply, resistor and plates, I used alligator clips. To ensure the highest accuracy for baseline, I used pure water which I obtained from the chemistry laboratory. Using high quality pure water was essential to minimize any initial ionic interference before we start adding the salt. I would like to especially thank the chemistry lab assistants for providing the pure water used in this experiment. After setting up the hardware, I followed a systematic procedure to collect the data. First, I filled the box with pure water using the DC power supply and I charged the capacitor to an initial voltage. I then disconnected the power supply and started the digital stopwatch exactly when the discharge began. I recorded the half-life time as the time it took for the voltage to drop. Then, to observe the dielectric decrement, I used the digital scale to add sodium chloride in 0.5 grams increments. After each addition, I stirred the solution thoroughly to ensure the salt was fully dissolved and density was uniform between the plates. Now let's look at what the numbers tell us. As you can see in table 1, the relationship is undeniable. At 0.0 grams, our half-life was 2.95 seconds, giving us a capacitance of 425.7 microfarads. But at 1.5 gram, the half-life dropped to 1.75 seconds, and the capacitance fell off to 252.5 microfarads. It represents a total 40.7% reduction in charge storage capability. When we plot this on a graph 1, we get a very strong linear correlation with a slope of minus 116.04 microfarad of grams. This slope effectively quantifies how the salt ions interfere with a water's dielectric permittivity. To conclude, our experiment clearly proves the dielectric decrement theory. By increasing the salt from 0.0 grams to 1.5 gram, we've measured the capacitance drop. The linear slope of minus 116.04 microfarad per gram shows exactly how sodium and chloride ions lock the water deposits into the solvation shells and lowering the permittivity. In short, ionic density is the K factor in reduction to liquid capacitance. A special thanks to the chemistry lab for the pure water. I'm Can Bey, and thanks for watching.